Hello everyone, my name is Qing. I'm from Southwest Jiaotong University. So I'm happy to make this presentation and the Informs annual meeting. My presentation title is Deep Learning for the Detection of and Recognition of the Real Defects in Ultrasound beat scan images. First part is the research background. In China, high-speed rail is very common. And Chinese high-speed rail network is the largest network in the world. It's around 2/3 of the entire world's mileage of network of high-speed rail. In China's high-speed rail, the existing construction challenges is for multi-climbed zooms with different maybe high temperatures, low temperatures, high wind, and we have complex geology challenges, diverse land forms. The operation challenge is how to efficiently maintain and a safe and efficient high-speed rail network. So the research significance is the rail part is the only part of the track structure that is in contact with the wheels and directly bears the load of the vehicle through the wheels. The structure and status of the high-speed rail have a significant impact on the operation safety and quality. So it is particularly urgent to realize the safety and long-term service of the high-speed rails. And existingly, China's railway are gradually shifting from large-scale design, construction to the long-term operational safety, management, and maintenance. So there are three engineering problems to be solved. The first one is the accuracy and the efficiency of the rail defect detection are very relatively low, and the unknown knowledge of the evolution of the track defects in complex environment is also very emergent. The last one is we don't know the maintenance rules of the rails need to be which need to be improved urgently. For the current development status of the smart rail, there are three trends. The first one is intelligent sensing and integration of IoT sensing. This can break the information islands of different departments, such as operations, maintenance, fraud detection, and to achieve a comprehensive perception of the rail and track operation status. The second one is how to fuse the multi-source heterogeneous data and carry out the fusion of the real multi-source operation and the maintenance related data based on the coupled sensor decomposition for identification and the early warning of the abnormal rail defects. The last one is service performance evaluation and maintenance through the life cycle of the rail. So the construction of the data-driven track repair, decision-making, and multi-objective optimization theory for the high-dimension state and decision space of track is very important. So here's our research equipment. So we have developed a dual rail defect detection equipment, and we also have several high-performance computing computers and also a big data Hadoop platform. For our equipment, our collaborator has developed a dual track defect detection and the rail service monitoring integrated detection vehicle. So this vehicle runs on two rails and consists of 4 people. And it has a relatively high speed, and then it can have a very long mileage rail defect detection. The rail defect detection system can detect the inside of the rail by ultrasound. And the defect detector can also view the rail surface images simultaneously when viewing the B-scan data. So for this system, there are 3 subsystems. The first one is called ultrasound defect detection system. Basically, is to use ultrasound to take pictures of the internal image of the rail defect of the rail, and then they call the A and B scan images. The second part is the real surface monitoring system. Basically, is taking pictures on the rail itself, mainly the internal side of the rail. The last part is the track inspection system, which adopts the computer and the machine vision technology to inspect not only the rail but also fasteners and the track plates and the track bed. So we developed a Euro 3 based algorithm for the B-scan images identification. So the existing big car and the detection rate is relatively low, only 80%, although the speed is high, around 80 kilometers per hour. The small hand-pushing real defect detector has a detection rate over 90%. However, the efficiency is very low. The speed is only 3 kilometers per hour. So that's why we developed our own dual rail inspection car. And here are the examples of the real defect dataset. We have two types of dataset. The first one is normal dataset, including the electric flash butt weld (EFBW), joint bolt hole sections. Those are normal images. The second part is abnormal dataset, including the detailed fracture (TDD), shell spalling conclusion (SSC), bolt hole break (BHB), and broken base (BB). So as you can see, different type of dataset, different type of defects are showing different pixels in the B-scan images. So we're trying to identify those pixels and to combine with the humans, very experienced real engineers experience. So we are using Euro 3 algorithm. Euro 3's algorithm is well adapted algorithm for the object detection. It is a one-state detection algorithm, and the advantage of this algorithm is it has a very fast speed and high precision. To achieve this B-scan image regulation, we further improved the Euro 3 algorithms, and in the following three aspects. The first one is in image pre-processing. We randomly copy the subsmall objects, and we developed 8 neighboring noise filter algorithm. The second one is backbone network improvements. We try to modify the residual network to improve the feature extraction capabilities. The last one is net network improvement. We add a minimal detection layer, SSPP modules and SE modules to improve the small scale object detection capabilities. Because for some defects, the pixel is very few. The number of pixels is very few, and it's a very small object in the B-scan image. We'll try to improve that capabilities. So here are the final results. Or the average MAP of this method is 88%, which kind of acceptable for our real defect detection. And except for the section of normal dataset, the AP for the other 3 categories are all above 90%. Due to the small size of the transverse fixture and the real bottom defects, and it is very difficult to detect. Others, the average accuracy is above 70%, and the rest are above 90%. So the challenge is to detect the TDD defect using B-scan images. Now we achieve 72%. So we still have a large room to improve in the future studies. And thank you for your attention. This is my email address.